Hi, my name is Julia, and I'm going to present the article Effect of Machine Pyramids on Codifiers during the endemic of UNSS 32205. The article was written by me, Julia Canistani, Eduardo Sperotto, Maurício Policena, and André Souza. We are from the Federal University of Rio Grande do Sul. Introduction. Duplex stainless steel is a low machinable alloy with a biphasic structure, 50% ferrite and 50% austenite, applied in oil, tanker tanks, flanges, and pipes. GSS are iron, chrome, and nickel alloys, and it has low thermal conductivity, high ductility, and boot-up edge formation. So the object of this study to investigate by box bank design the influence of the cutting speed, feet per tooth, actual depth of cut, and two nose rates and their interactions on the static and dynamic portions of the active and passive force in the foot and mill of duplex stainless steel. The figure 1 shows the example of the application of the duplex stainless steel. Material and methods. The chemical composition of duplex stainless steel sheet supplied by Otto Company was obtained by the Booker Q2 ion, and after compared with the SECM A240 standard, Table presents the results of the analysis before. Metallograph analyses were performed with a Z-scope A1 option microscope. The specimens were prepared with Ferrara X. The figure 2 shows the microstructure composed of austenite and ferrite. The image indicates one equilibrium between the two phases. The image shows the ferrite materials and present the austenite island. The end milling were performed by Romy Discovery 308. During the machine, a Butman BD fluid B9003 was used in the abundance condition. In its plate, 634 runs were performed using different combinations. So the figure 3 showed the experiment setup. The figure 4 showed the force acquisition system, during which run the orthogonal components were collected according to the image. The carbide insets were vaulted to this model. Three different nose rates were used: 0.4, 0.8, and 1.2 millimeters. They were used with a Walter Tools milling head. So the analysis, the static and dynamic portions, it was used the equation 1 and equation 2. Thus, the static portion expressed the mean value of the force considered the stable interval that excludes the unstable regions of the entry and exit of the mini-courier, while the dynamic portion constitutes the force fluctuation. The table 2 shows the natural levels of the box bank design factors. It was used 3 levels: low, medium, and right, for the 4 control factors. Results and discussions. Table 3 illustrates the values for the static and dynamic portions of active and passive force during the end milli of duplicate stainless steel for 27 combinations determined by box bank design. The figure 6 shows the static and dynamic portions of active force. The smallest values of active force occur during run 1 for both static and dynamic portions because it has the smallest cross-section area. If the depth of cut and to-nose ratio is 0.5, the highest values were generated in run 13 with depth of cut and to-nose ratio is 1.5. Santos and Sally explain that by increased feet per tooth and depth of cut, the forces rise directly, almost linear, due to increase in primary and secondary shear zone during cuts. So the figure 6 shows the smallest and higher values for the active force. In 3 runs, 6, 22 and 24, the dynamic portion of the active force was higher than the static portion, which indicates high force fluctuation, and these runs were at the same level. Feet per tooth is 0.06 millimeters per tooth. Thus, the dynamic portion is about 20% larger than the static portion in run 6, while the percentile increase was minor in run 22. The figure 7 shows the static and dynamic portions of passive force. Figure 7 presents that run 17 generates the lowest value of passive force for the static portion. The lowest dynamic portion was also measured in run 1. In the both runs 1 and 7, to-nose rate is 0.4 millimeters was used. The highest values of static and dynamic portion were obtained in run 21, with depth of cut and to-nose ratio is 1.0. Therefore, it was noted that the ratio has different effects of the active and passive mini force. Run 9 stood out in the experimentation for present strong stability vibrations in the end milli process. As a result, severe tipping on the thread occurred during curing. However, the data samples were considered before fracture. In this case, the dynamic portion was higher than the static portion by 102% for active force and 296% for passive force. Soria explains that the lower the depth of cut and to-nose ratio, the greater the force in the axial direction. That tends to push the two heads away from the curing region, tend to increase vibration. So this figure 8 shows the first size during the milling, and 8b shows the two states of the machine. The variance analysis was obtained in this study. The analysis shows that feet per tooth to nose rates and depth of cut to nose rate ratio were significant for the static and dynamic portions for the active force. The cutting speed and two nose rates were partially significant for the static portion, the passive force. Control plots were generated to visualize the relationship of the active and passive force with the control input factors. The analysis specifies above produced the control plots based on the adopted input parameters levels. The influence of the main factors on the behavior of the force was evaluated. Smaller force values result from low levels of action, depth of cut, and feet per tooth. These combinations correspond to a smaller cross-section, which agrees with the theory presented in this study, and the results obtained through variance analysis. The influence of cutting speed on static portion of the active force could also be seen. On the other hand, there was no influence from cutting speed and dynamic portion of the passive force generated during the end mill of UNS at 322L5. After analyzing the active and passive force values, the best control factor arrangement was determined to optimize the responsive variables. Figure 10 shows the values for the best combination of current parameters, this, and the estimated values for the responsible variables to the active and passive force. The values this and the function d, composite disability, indicates the desired value of the predict date for the combination variables. The code to run degrades the probability that they will be obtained. In this work, the value d is 0.9306. Conclusions. The lowest value of active force occurs in run 1 because it has the smaller cross-section area. The highest value was generated in run 13. Run 17 generates the lowest value of the static portion of the passive force. The lowest dynamic portion was also generated by run 1. In the both runs, it was used to nose rate is 0.4 millimeters. The highest value of passive force occurred in under run 21. Run 9 showed strong vibrations in the end middle process. The opposite control factors to generate the lowest active and passive force values were speeding, cut 110 meters per minute. Depth of cut is 0.2 millimeters. Feet per tooth is 0.072 millimeters per tooth, and the to nose rate is 0.4 millimeters. Acknowledgement. The authorities thank CNPq for the student scholarship, Autocomp Company for donation of material, Walter Tools Company for the tools, Woodman Company for the current food, Foundry Laboratory for the chemical composition analysis, UPF Park for the metallograph analysis. Thank you.